Let's talk about the no free lunch theorem. So we just covered bias variance trade-off. And bias variance trade-off was about model complexity, but not only we have models of different complexity from the same model class, but we can also have models from different classes, like logistic regression or support vector machine or perceptron. Which one to choose, right? We could think about millions of different models and variations of them. Wouldn't it be nice instead of doing that? Because sometimes a machine learning course feels like just an inventory of different algorithms, and like when I don't think about it, it feels to me, okay, well, it's like a bookshelf. I have tons of options, and I just need to know which option apply, like which problem, like which option or which algorithm applies to which kind of live situation, right? So it feels like, or it can feel that machine learning is in a sense a recipe book. Pick one, pick another. Well, of course, recipe book cannot be used, or can be more efficiently used if you understand why pick one versus another. But couldn't we publish one model once and for all and forget about what's happening in the world, of other models, and don't know the details? And but that would be of course nice, because it would be nice even for industry. That would be a saver. Then we wouldn't need any data scientists or machine learners or anyone. There will be a model that you just train on your data, and that's it, that you're guaranteed to have the best model ever. And the tricky part is that machine learning is experimental science, and as an experimental science, we don't have the power of inductive reasoning as we would have in mathematics, say, because we never fully know the generative process of the data that comes to us. And if we knew, then we could predict the result, or actually generate the result ourselves. So we wouldn't need to go in the wild and do any experiments. What I mean by that, for example, say we're building our classifier or a predictive model, diagnostic model for some medical condition. If we knew exactly how, by looking at, not looking at anything, how would a CT of say tuberculosis look like, or coronavirus, then we wouldn't need to train any model. We would just write a set of rules. Okay, this is how it looks like, or we would just generate it and match. Does it match or not? But usually we don't fully know the generative process. We don't know how CT of a person with coronavirus will look like at any given moment for any given person in any given place in the world, for any given strain, right? So we will have to assume and conduct experiments that the data that we've seen so far generalizes. That means if we've seen some sequence of or a set of data examples, let's go here, David Hume, and the examples would be X and Y, as you remember, right, where X is our feature vector and Y is our label. So once we're here in this regime and we collected lots of data, which we did in the following way. It's a set. We could assume we've seen everything, and the next ones will be just like that. But unfortunately, as David Hume put it back in the day, even after the observation of the frequent conjunction of objects, we have no reason to draw any inference concerning any object beyond those of which we have had experience. Well, that's a very strong statement, I would say. And that statement was used by a man who we owe to the no free lunch theorem in all of its version, is David Wolpert. You see him here. So remember our function f labeling function from the beginning of the class, from the beginning of the semester in the computational learning theory part. So that function assigns labels to examples. So this is our target or label assignment function. If this function is totally arbitrary, or we cannot know anything about it, or it is uniformly sampled from all possible labeling functions, then for any two algorithms A and B, there are as many targets for which A has lower expected generalization error than B, and vice versa for loss functions like 0-1 loss, which is classification, right? And equivalently in optimization, or for our purpose on a high level, the statement goes as for any two algorithms, and I'm here right now, for any two algorithms, any elevated performance over one class of problems is offset by performance over another class. Well, that's sad, right? Well, luckily, of course, it does mean that there is not a universally good algorithm that's best for all possible test data. But it also means we are an experimental science. We can conduct experiments. We can choose our priors. Are basically what the no free lunch theorem says. We have to choose our priors. We have to assume what kind of data we will encounter in the wild. What will be the test data set? What do we have to generalize to? And certain algorithms will work for certain kind of data, and other algorithms will work better for other kinds of data, and well, which is good.